Okay, so that's my goal today, to get to, for those sort of topics that are on the front of that page, along with copies of these notes. All right, so what did we talk about yesterday, or better yet, what did I talk about yesterday? We started with the idea that if we take a primary or a secondary alkyl halide and we react it with a nucleophile, and we're going to find out today that that nucleophile has to be strong. So what's a strong nucleophile? One that has a negative charge. That if we do that, the kinetics said that the rate of that reaction was equal to a rate constant times the concentration of the alkyl halide to the first power times the concentration of the nucleophile to the first power as well. So the reaction was first order in nucleophile, first order in alkyl halide, and then we called that overall then a second order reaction. And a second order reaction then means that in the mechanism we have two molecules reacting together, which is the alkyl halide and the nucleophile, which makes this a bimolecular reaction. And so when we react to alkyl halide with our nucleophile, we substitute then the halogen for the nucleophile. We've now reacted a nucleophile, generated a nucleophile on the other end, and that then becomes nucleophilic substitution that's bimolecular, which means that we abbreviate that as SN2. And as far as the stereochemistry goes, the stereochemistry of the reaction, if this alkyl halide is a chiral molecule, if it's one enantiomer, the reaction's going to go by an inversion of configuration. So if the nucleophile, or so that if the alkyl halide starts out R, it becomes S, or vice versa. And the last thing is, what's the mechanism? So if we took a hydroxide and added to that ethyl chloride, the first step is to show that the electrons from the OH come in and add to the carbon. So we used a curve arrow to add to the carbon that's attached to the leaving group. And then we have a second arrow from the chlorine going to from the carbon-chlorine bond going then to the halogen. So that's the first set of arrows that we need to draw, showing this pair of electrons adding to the carbon and the chlorine reacting. All right, so what's the transition state going to look like? The transition state is always going to look like this. You're going to have a carbon with dotted lines where the nucleophile comes in. I normally write it from the left, and then the leaving group on the right. And then the other three positions are going to be the positions of are going to be the 3 positions that were originally in this carbon. So this carbon has a hydrogen, another hydrogen, and then the methyl group attached to it. So that's where those will go. And what I'm drawing here, let's see if I can. So the 2 hydrogens in the methyl group. The chlorine then is the leaving group, and the hydroxide is the nucleophile, so they go on dashed lines. This bond right here, because I've got too many dashed bonds, I'm showing it as like a dashed wedge. I know, it's hard to see, but it should look like that, as a dashed wedge, to differentiate it between a dashed line.
Okay, which one is the dash?
Let me see if I can write it bigger here. So I got the C with the H, then I've got a bold wedge, and then I've got a dashed wedge. And it doesn't matter where you put the hydrogens in the methyl group from the ethyl group. You can put them on any one of those 3, as long as that's just like a Newman projection. It's got to have 2 H's and a methyl. And then the dashed lines go to the chlorine that's leaving, and the dashed lines go to the hydroxide that's coming in.
So there's 5 bonds on that carbon.
Right. So what we said yesterday was that normally, if those were 5 complete bonds, we'd be violating the 4 bonds to a carbon rule.
That's why it's a dash.
Right. These are partial bonds. So as the hydroxide comes in and adds to the carbon,
Which ones are the partial bonds?
these ones, the dashed lines.
Okay.
So these are the partial bonds. There and there. So as the hydroxide comes in and forms a bond to the carbon-chlorine bond has to be breaking at the same time. And so in this transition state, this bond over here is being formed, that bond's being broken.
So the methyl group one, that's not a partial.
No, that's a stereochemistry, like we have our bold and dashed wedges to show R and S.
Okay.
Cameron?
In this picture, are the dashed lines to show orientation, or are they to show the partial bonds?
So they're there to show the partial bonds.
Okay.
But those partial bonds are in the plane of the paper.
Okay.
They're in the plane of the paper. So the carbon then, what happens is this carbon then becomes trigonal bipyramidal. And so normally we've shown trigonal bipyramidal as having the positions that are linear up and down, and all I've done is I've just moved them so that now they're horizontal. So this is the partial bond forming between the O and the C. This is the partial bond between the C and the Cl that's breaking. And then so that when the hydroxide comes in and adds to that carbon, and the carbon-chlorine bond breaks, those 3 bonds that are pointing, let's see, this way according to your orientation, as the hydroxide gets closer and closer, they flatten out until you get them perfectly in the middle with the transition state. And then as the chloride leaves, those bonds are going to then go from being flat to then moving so that we invert the chiral center. So this is the transition state. That's the high energy species. What I'm missing here, though, are the charges. So let's write the products on the other side. So on the other side, the hydroxide is going to be attached to the carbon. And now the chiral center will have been inverted so that the hydrogens in the methyl now go from being oriented to the left to being perpendicular to then being oriented to the right, which is how the molecule would go from being R to S if this was a chiral molecule to begin with. And the chlorine then would be a -1 charge. So in the transition state, basically what you see me doing in the transition state is what we did with the resonance hybrid a couple weeks ago. The transition state is the average between the reactant and the product. So if we look at this, then we have no carbon-oxygen bond on the left in the reactant, and in the right we have a carbon-oxygen bond, so the average of that is a partial oxygen-carbon bond. In the ethyl chloride we have a carbon-chlorine bond. In the product we have no carbon-chlorine bond, so what's the average? A partial carbon-chlorine bond.
So for the final one, the methyl group, is that just a dash thing?
Yeah, it's a dash behind.
It doesn't stand for partial bond.
No, it's a dashed wedge, yes.
Okay.
It's a dashed wedge. That's the best I can do for a dotted line. So I'm averaging the bonds just like I did for resonance hybrid. And now I have to average the charges. So the OH, the O in the OH goes from -1 to 0. So in the transition state, the oxygen is partially negative. And then on the other side, the chlorine is going from 0 to being -1, so its charge is delta minus. So in this mechanism, what's happening is the hydroxide's attacking the carbon, the bonds are basically going and flattening out, and then they're reversing themselves on the other side. And yesterday I kind of said that would be like an umbrella blowing itself inside out, is the way you could look at these three groups. But, well, it'd have to look like this. There's your handle to your umbrella. There it is. Over here on the other side, there's your handle, and your umbrella's blown inside out. So also what's happening then is, always in transition states, we're either making bonds or breaking bonds or doing both. And that's what the dotted lines represent, the making and the breaking of the bonds. And then the charges in this case are that the hydroxide is going from being negative to neutral, and so what's happening is the charge is being transferred then from the hydroxide to the chlorine on the other side. Now it's not really transferred because the O is forming the bond with its electron density, and the chlorine is taking its electron density from the carbon on the other side. So it's not like the electrons are flowing from O to Cl. It's just that the O's using it to bond, and the chlorine is taking whatever remains in this polar covalent bond is taking it away to form the Cl minus. So that's how we would write the transition state for that reaction, and we have to be able to write the transition state. But in an SN2 reaction, since it's a one-step concerted mechanism, this is the mechanism, this one step. So since you're probably concerned about, well, what will I have to do next Monday, right? Because that's what most people are concerned about. You would say, you got to make sure you show the nucleophile adding to the carbon that arrow and the arrow going to the leaving group, showing the proper transition state, and then on the other side of the molecule showing the correct product and the Cl minus. So this is just a one-step mechanism. And how did we know that? Because that's what the kinetics told us, because in the one-step mechanistic step, it has to be bimolecular, and so this makes sense. And then looking at the stereochemistry and the inversion of configuration, that told us also that it makes sense that it's a one-step mechanism and that it's backside attack. Right? So that's what we did yesterday. And today we'll get a little time and we can start writing the mechanisms, or maybe I need to take that. Maybe I need to make that a take-home quiz, which I can certainly do by the end of the day. So that's what we want to do. So what's going to be different today? Well, if you can imagine that someone who used a primary or secondary halide did this reaction with the hydroxide, saw it was overall second order kinetics. They then said, well, let's try it with the tertiary halide. So I'll try it with something like tertiary butyl chloride, and I'm going to add a hydroxide to that. So they did it with primary, found out it was bimolecular kinetics. They did it with secondary, same thing. Now they do it with the tertiary. And so if we have a substitution, we're going to have the OH substitute for the chloride. So same reaction. We get the same products. But when I looked at changing the concentrations here, when I started out with like maybe 1 molar, 1 molar, with 1 molar and 1 molar, I got a rate constant, let's say, of 1. So then what they did was then they said, well, let's take the alkyl halide, let's double its concentration, hold the concentration of the hydroxide present, and their rate doubled. So they said, oh, well, okay, in terms of my rate equation, I know that this is now first order in alkyl halide. They might have checked that by making it 3 times the concentration, and the rate increased by 3 times the initial rate. So they found that in alkyl halide, the rate was first order. But then, when they said, well, let's go back to the original alkyl halide concentration, and now let's double the concentration of hydroxide, they found out that the rate didn't change. And then they tripled the concentration of hydroxide, and the rate didn't change. And they probably made it 10 times higher, and the rate still didn't change. So they found out that the rate wasn't dependent on the hydroxide concentration. And then they probably changed it to some other nucleophile and found out the rate didn't change there either. So what we could write the rate equation then to be is that what would be the order of the nucleophile if the rate doesn't change? 0. Because anything to the 0 power is 1. So that means that the rate, basically, the rate equation boiled down to only being dependent on the concentration of the alkyl halide to the first power. And so if they did this, the first thing that they would probably do is go, why? But before they said, you know, okay, why, and they did all the experiments and verified it, their first conclusion would be the mechanism has to change, going from primary and secondary to tertiary. I'm dealing with a new mechanism here because the kinetics are different. And back in general chemistry, if you had, you know, any doubt about, well, why is kinetics useful? It's useful for a number of reasons, like how long is it going to take for the reaction to go to completion? An hour, a minute, a day, 10 days, never. The other thing is then that tells you if you have a mechanism change. So the mechanism has changed. So now you have to go back and you have to think about, okay, if the mechanism changes, I need to propose one. And I need to propose one where the mechanistic step, its rate is only dependent on the alkyl halide and not the nucleophile. So ultimately, what was decided was that here's how the reaction occurs. I take my alkyl halide, and in this case, I'm going to have 3 alkyl groups. And I'm going to take that alkyl halide, and I'm first going to break the carbon-chlorine bond. Just for fun here, because you're going to have to do this, let's write the transition state for this reaction. Well, before I get to the transition state, what are the final products? Well, if the chlorine decides to break up with the carbon, and the chlorine decides to take with it both electrons, that's called heterolytic bond cleavage, because both electrons are going to the chlorine. And does chlorine have the power to do that? It does, because it's more electronegative than carbon. So it's going to take both the electrons. That's going to leave the carbon with losing an electron, which means that carbon then is going to have a positive charge. It's sharing 6. It owns 3. It came with 4 plus 1 formal charge. And this is what's called a carbocation. It's also sometimes called a carbonium ion. Although I prefer strictly carbocation. And so that's what we would get if the carbon-chlorine bond breaks heterolytically. Can it break so that each atom gets an electron? Yes, but that's next. That's organic too in this book. So what would the transition state of this reaction look like? Well, to write the transition state, I'm going to write the species. And then a dotted line goes to the bond that was broken, or the bond that was formed, but in this step, I'm only breaking a bond. So where should the dotted line go? Between the carbon and the chlorine. Okay, so there's my dotted line, which means in the transition state, I've got a partial bond because the carbon-chlorine bond is breaking. How about charges? which atom should get which charge.
They both have-
One will be negative. They both can't be negative. So remember, we're going to average. So let's look at the carbon. On the left, what's the charge on the carbon?
0.
On the right, +1, carbon, delta plus. So the carbon is delta plus because it's on its way to a positive charge. The chlorine then would be delta minus. Now, the other reason that those two atoms can't be delta minus is because overall the charges add up to 0. Up here, overall the charges on both sides are -1. So that's why we could have two negative charges, two delta minus charges in the SN2 reaction, but here they have to be neutral. They have to basically cancel each other out. So what's happening in the transition state? I'm breaking the carbon-chlorine bond, it gets a dotted line. Carbon's becoming positive, chlorine's becoming negative, carbon delta plus, chlorine delta minus. Okay, so there's the transition state. And transition states are written in brackets with the double dagger to indicate that they are transition states. Okay, so in step number 1 here, I formed my carbocation. Now, if you're a mechanistic chemist, and this is the first time you've proposed that species, I'm going to need to show that it can exist. I'm not sure if anybody had shown that this actually exists to begin with. But could it exist? If somebody's going to ultimately buy this mechanism, and this mechanism's been bought, sold, I mean, any mechanism that shows up in an organic book has to go through all sorts of scientific validation. I mean, if it shows up in a paper and then multiple papers over decades, it shows up in a textbook. So this has been shown. Carbocations, we can actually, well, we'll talk about what they are, but they exist. Sometimes for only a little bit of time, sometimes they can form and stay for a lot more time. So this is step 1. Now, if I said, what's the rate of this equation? So in the mechanistic step, I can write the rate equation based on the stoichiometric coefficients. Remember, in the overall reaction, I have to determine experimentally. But when I'm proposing mechanistic steps, I could say, well, the rate of this reaction is equal to a rate constant times the concentration of the reactants, which in this case is going to be my R3CCl raised to the what power? 1, because there's a stoichiometric coefficient of 1. And so that rate equation that I can write for this first mechanistic step, what does it look like? It looks like the overall reaction. Which there was probably a lot of trial and error that went into this. And the trial and error would have ended if that mechanistic step did not have a rate equation equal to the overall equation. So that's step 1. We okay with that? So then what happens in step 2? So in step 2, I've just made a carbocation. What's a carbocation? Electrophile or nucleophile? Electrophile. Is it electron rich or electron poor? Poor. Because it's got a plus charge. So this is one of the extremes of an electrophile. Not a delta positive charge, but a full-blown positive 1 charge. So this now is an electrophile. So electrophiles react with nucleophiles. My nucleophile then, you could say, well, how about the chlorine? Yeah, I mean, the chlorine could come back and add, but that doesn't get me towards the product. Or if I used a lot of excess hydroxide, it's the hydroxide now that's going to be my nucleophile. Strong nucleophile with a negative charge. Those two are going to react together. The hydroxides, lone pairs, that are giving it its negative charge are going to then, it's going to donate a lone pair to the C+, and they're going to go ahead and share that and form the chemical bond. So in my final product, I'm going to form my substitution product, where I've now added the hydroxide, formed the CO bond. So this is step 2. Nucleophile reacts with the carbocation. What's the transition state for that going to look like? Am I forming a bond? Yes. Between the C and the O. So that's where the dotted line should go. So the CO dotted line, so that's where the bond is forming. The OC bond is forming. And any charges in that transition state? On? Okay, so what partial charge goes on the carbon? And on the oxygen? A negative. Because the carbon is on its way, it's going from plus over here to 0 over here. The oxygen is going from -1 to 0 in terms of its charge. And so carbon delta positive, oxygen delta negative in that transition state. So in this case, what we've seen is 2 transition states. One for breaking the bond and one for making the bond. But in this mechanism, those are 2 different steps. So what would the rate equation for this mechanistic step be? It would be that the rate equals the concentration of the carbocation times the concentration of hydroxide. And stoichiometrically, it's 1 to 1. So that rate equation of that step would be carbocation concentration times the concentration of the hydroxide. Now you might say, well, how do you measure the concentration of the carbocation? Well, the carbocation basically comes from the original alkyl halide molecule, so I'd have to basically do a substitution on that. But what's critical here is that this mechanistic step has the hydroxide in the rate equation. So I've just written 2 steps. in the mechanism. Hannah?
So is this part of SN2?
This is actually an SN1. This is going to be an SN1 reaction, but I haven't said why it's 1. So in SN2, it was a concerted one-step mechanism. Nucleophile comes in, kicks off the leaving group. We form that transition state where the bonds are being made and broken in one step. This is different because when we did this reaction with the tertiary halide, we found out that it was 0 order in nucleophile, so the nucleophile concentration didn't affect the rate at all. So now I'm trying to come up with a mechanism that explains that kinetics. So that's where I'm at. So I now have 2 steps in my mechanism. The first mechanistic step is to break the carbon-halogen bond to form the carbocation. And I'm simplifying it here. But that's the first step. And in this rate equation, the rate is equal to the concentration. The rate's dependent on the concentration of the alkyl halide to the first power. Then in the second step, the carbocation reacts with the nucleophile to form the final product, and that rate of that elementary step would be dependent on the concentration of the carbocation to the first power times the concentration of the nucleophile to the first power as well. And if I take these 2 mechanistic steps and I add them together, what do I get? Alkyl halide plus nucleophile makes product plus X minus. And that's our overall reaction. So this is the accepted mechanism for the reaction of a tertiary halide. Why? And there's another term we need to define, which we can do by these mechanistic steps. There's actually multiple terms. So in our energy diagram from yesterday, we went from the reactants up to the transition state down to the products in one step. What happens when we have 2 steps? How's the energy diagram going to change?
2 humps.
It's going to have 2 humps and a valley. So that energy diagram is going to go up through a transition state, which we wrote up here, or which we wrote on the last page. That was transition state 1 to break the bond. Then what do we form? The carbocation. And then we go through a second transition state and then down to the products. So there's our reactants, there's our products, there's transition state 1, there's transition state 2, bless you, and there's the carbocation, that's the valley. Now I know a few things in order to write this diagram. First of all, whenever you're making and breaking bonds, those are going to be the transition states. And transition states are always higher in energy than anything else. This carbocation is unstable relative to the reactants and the products. Right? Why is the carbocation unstable? Okay, that's true. It's more stable because it has more energy. Why does it have more energy? In other words, why is it more unstable? It does have a positive charge. It is going through a change. What's making the carbocation unstable? It has 3 bonds. How many? Keep going.
It's reactive.
Okay, I like the 3 bonds though. We're getting closer. It wants 4. Why does it want 4? Because the octet rule. Right? Does that carbon have an octet in a carbocation? No. Right? So it all goes back to the octet rule that we started with for Lewis structures. So a carbocation is unstable because it basically is sharing 6 electrons and it would love to have 8 electrons. So the carbocation then has a higher energy than the reactants and products, which is why it's above the reactants and products on the diagram. And we're going to have to talk in a minute here about carbocations and how we can make them more or less stable. But we'll get there. Now, how about these two mechanistic steps together? When I look at this, why doesn't R plus show up? Why doesn't the carbocation show up in the overall reaction? On the one side, it's in the products, and on the other side, it's in the reactants. So it cancels out. What do we call species that show up on both sides of the reaction? They're products and reactants in a mechanism. They're called intermediates. So the carbocation then is an intermediate. Since it's produced in one step of the mechanism, this is the technical definition. It's produced in one step of the mechanism and is reacted in another step of the mechanism, so net it doesn't show up in the overall reaction. So that's the intermediate. Now, what's the difference between an intermediate who has high energy and a transition state that has high energy? I can make that a rhetorical question. So if it's a transition state, it only exists for a very short time. And the real thing is, can I put a transition state in a bottle? Can I study it? No. But what about intermediates? Intermediates, it is potentially possible to study those. They have varying lifetimes, but it is possible that I might be able to put a carbocation in a bottle and study it. So intermediates, because they're lower in energy than a transition state, they might be able to be studied. And there are intermediates, not necessarily a carbocation intermediate, but an intermediate that, for instance, has an unpaired electron called a radical. And I think the most famous one of those was put in a bottle back in the early 1900s, and then about 1960 they went back with the same bottle and opened it up and then studied what it was. And it turned out to be a carbon with an unpaired electron. So they can exist a long time if necessary, depending on exactly which one it is. So the difference between intermediates and transition states, I can't isolate a transition state, but I might be able to isolate an intermediate. right? And they're smaller in energy as this energy coordinate, as this reaction coordinate diagram shows. So they're more stable. Okay with that? Next thing we need to talk about with these mechanistic steps. Do they have to occur at the same time? Or sorry, do they have to occur with the same rate? No. One could be faster than the other, and that would make one slower than the other. So one might take a day and the other one might take a minute. What's the overall rate going to depend on? The slowest one. What do we call that step? The rate limiting step or the rate determining step. So the slow step in the mechanism is called the rate determining step. Why is the rate determining step important? Because if I'm trying to determine the mechanism of a reaction, the rate equation from the rate determining step is going to equal the overall rate equation of the reaction. Okay. So the slow step is going to give me the overall rate of the reaction. And so its rate equation that I can write based on stoichiometry is going to equal the overall rate equation. So in this step, or in this mechanism of step 1 or step 2, which one is the rate determining step? Which one has the rate equation that equals the overall rate equation? Step number? I had to determine the overall rate equation experimentally. But when I'm talking about the mechanistic steps, I'm allowed to use stoichiometry. So I forget, apparently you do too. What's the overall rate equation for this reaction? What's it dependent on? Is it dependent on the concentration of the alkyl halide? Yes. What's it not dependent on? The concentration of the nucleophile. So, given step 1 and step 2 here, whose rate equation looks like the overall rate equation? Step number 1. So what's step number 1? The rate determining step or the slow step. So this is the rate determining step, or it is also the slow step. What about rate 2? Or step 2? Step 2 is the fast step, relatively speaking. So in other words, we wait for the carbocation to form. We're waiting. It forms. Nucleophile adds. So this is how we do the mechanistic study. We determine the overall rate equation. The overall rate equation says, hey, something changed. This doesn't have the same mechanism as a primary or secondary. So then we go off, we try and search for it, and we start proposing mechanisms. Again, trying to propose simplest mechanisms because that's usually the way nature works. Although there are reactions where it doesn't work that way. If you search, like, there's one called the iodine clock reaction, where when you mix these things together, it goes from being a clear solution to being like pitch black, and then it goes back to clear again, then it goes back. I think that's 26 steps. Somebody trying to figured out what the steps were, and it was like 26. But that's the exception to the rule. Most of these are very small steps because we tend to make things simplified. We, nature, etc. So in this case, it's a two-step mechanism. Slow step to form the carbocation. As soon as the carbocation forms, it instantly reacts with the nucleophile.
Are you going to expect us to have to write our own mechanisms?
Oh, absolutely. Absolutely. I mean, that's going to be the next test. You're going to have to write products. You're going to have to write the mechanisms. Yeah, we don't skip mechanisms. The reason we don't is because organic chemistry, okay, what makes organic chemistry not impossible? The idea that we can group groups together like alcohols or like alkenes, and they all tend to react the same or pretty much the same, except for a couple minor details. But for the most part, we can group the atoms together into what we call functional groups, and we can learn the reactions that way. The other thing is that many of these mechanisms are almost identical. And these mechanisms that we talk about, SN1, SN2, E1, and E2, these are the big ones. Well, they're the big ones to begin with in the first semester. And so we have to have a good understanding of those because we're going to be using these over and over again. If you go to biochemistry, you're going to be doing these over and over again as well. And just as an aside, we talked about, yesterday we used something like methyl chloride, and we'll talk about why methyl iodide is a better, undergoes a faster SN2 reaction. It's because iodide is a better leaving group, and so we need to define what makes a good leaving group. Methyl iodide is really toxic. And you might say, well, why? Well, if you get methyl iodine in your biological system, there's lots of nucleophiles around. Any OH group, any NH group are going to act as nucleophiles. And so what's going to happen is that those OH and NH groups are going to be able to attack that carbon and kick off the iodine, and so you're doing an SN2 reaction. Now, if that OH group or that NH2 group is part of an enzyme or part of DNA or RNA, then you're going to be mutating things. Then in general, mutating things is bad. I mean, I'd go for the mutation that would give me like superpowers of, I don't know, dishes and cleaning and laundry would be my top 3. If I could have those superpowers, yeah, go ahead and mutate my DNA all you want. But usually it doesn't end up that way, right? We end up with 3-headed fish and all sorts of bad things. Why? Why does that occur in the biological system? Because this undergoes SN2. And why does it undergo SN2? Why is methyl chloride a little bit better than methyl iodide? Because chlorine is actually not as good of a leaving group as iodine. And we'll talk about that today. So we need to know those mechanisms because in biochemistry, those mechanisms still show up. It's just on really complicated molecules. So yes, we have to write mechanisms, and we will. And usually I will give those at first try as like in class, second try, take home quiz problem, third try exam. Okay. So yes, you will have to write it, but we'll go through that in a few minutes as well. Right now we're laying down the basics. All right, so where were we at? And what was my point? So now for this reaction of a tertiary halide with a nucleophile, we found out that it's 2 steps. That it is not dependent on, the rate is not dependent on the nucleophile concentration. The rate's only dependent on the halide concentration. In the slow step of the mechanism, how many molecules are reacting? In the slow step of the mechanism, only one molecule is reacting. Hence, the first order. So what kind of molecularity is that reaction? Well, anything that involves reaction of a single molecule is going to be called a unimolecular reaction. And why is that important? Because when I look at this overall reaction down here, this is still SN. It's still nucleophilic substitution. I'm substituting one nucleophile with another. But now it has unimolecular kinetics, so now it becomes an SN1 reaction. So an SN2 reaction involved the kinetics of nucleophile and alkyl halide. SN1 is only dependent on the concentration of the alkyl halide. So at the end of class yesterday, I showed you that terse butyl group attached to the carbon with a methyl that was secondary, and I said, well, the nucleophile is going to have a hard time doing a backside attack on that. And then somebody asked, and I think it was Hannah asked, well, does it still go by SN2? Does the reaction go? And now the answer could be, yeah, it still goes, but it might go by an SN1 mechanism, not SN2, because I'd get the same product. And unless I measured the kinetics, I wouldn't know if it was unimolecular or bimolecular. But that's one of the ways I could tell. If I doubled the concentration of the nucleophile and the rate didn't double, it would be SN1. If the rate did double, it would be SN2. If the rate was somewhat in between, then what I've got is I've got some molecules doing SN1, some molecules doing SN2. Everybody with me so far? So this is what happens with a tertiary halide. Does this happen with a secondary halide? It could. Does this happen with a primary halide? No. Why do I say that? Because now what we need to spend a minute or two or 5 is on how does the alkyl halide, how many alkyl halide, or how many alkyl groups, or what's the role of the alkyl group when it is attached to a carbocation? What does it do? And it stabilizes the carbocation. So let's write out a C plus, and then let's add an alkyl group to it. So I'm like a methyl group. How does a methyl group stabilize a carbocation? Well, how do I stabilize that carbocation anyway? Right now it's got 6 electrons. What's it want to have? 8. So anything I can do to push electron density into that C plus is going to stabilize it. Attach a chlorine to that C plus, that's not helpful, because the chlorine is going to take away electron density and make it less stable. But if I add an alkyl group, I'm going to push electron density in. How? Carbon and hydrogen are very similar in electronegativities, but they're not exactly the same. Carbon is more electronegative than hydrogen. Carbon has an electronegativity of 2.4, hydrogen 2.1. How do I know that? I've been doing this a long time. So those numbers are seared into my head. So carbon is more electronegative than hydrogen. So what does that mean? We're treating carbon-hydrogen bonds as if they're relatively nonpolar, but now I'm going to invoke and say, well, there's a little bit of polarity there. So the carbon then is going to be delta what, and the hydrogens are going to be delta what? Delta minus for carbon and delta plus for the hydrogen. So anytime you have an alkyl group, the carbon is going to have a little bit of electron density. Where did it get it? From the hydrogens. So now that carbon has a little bit of electron density, what can it do with that? It can share it with that C+. So instead of the carbon having a +6 charge, or sorry, a +1 charge, maybe now it's down to like 0.8 positive. That's not enough. One carbon attached to a C+ isn't enough to stabilize it. So a primary carbocation is not going to form in solution. Because I'm going to take all that back next semester when we talk about mass spectrometry in lab. And we're going to be writing primary carbocations left and right. But in this class, rule number 3, right? Don't take the class if you don't have to. Don't write 5 bonds to a carbon. Don't write primary carbocations because they do not exist in solution. They're not stable. Why are they not stable? Because one carbon's not enough to stabilize that C+. Okay, how about 2? How about 2 carbons? Yes. A secondary carbocation is stable. So it takes at least 2 carbons to form a stable carbocation. Primary carbocations don't exist. And if you write a primary carbocation in a problem or on an exam, I usually write, oh no, a primary carbocation, parenthesis, or a couple of explanation points, followed by an X. So primary carbocations don't exist in solution. Can they exist in a high energy environment like the gas phase with a lot of heat? Yes. And that's what happens in mass spectrometry. But we're talking about solution reactions. So primary carbocations don't form. Secondary carbocations can form. What would be better? To add the third carbon to this, and if I add a third carbon or third alkyl group to this, now all of a sudden that tertiary carbocation is the most stable. Unless I do some other things, which we'll get to. So now, and has this been shown? Yes, it's been shown. Can I put a tertiary carbocation in a bottle? Yeah, but it'll last long enough to study it, but if I use really fast methods. It's not like it's going to last in a bottle for 90 years the way a radical did. So, an SN1 mechanism, we can think of this a couple of ways. SN1 and SN2 are complementary. If you have a primary alkyl halide, that means you have one alkyl group, 2 hydrogens, no steric hindrance on the backside, so the nucleophile can come in, attack, kick off the leaving group, and do SN2. And I give molecules human characteristics, which is not the case. But if they had them, nucleophiles, negative nucleophiles always want to form bonds and they always want to attack. So primary, no problem. It can do SN2. Tertiary, it can't attack because there's too much steric hindrance. So what happens? It's got to wait for the carbon, for the tertiary carbon to lose its leaving group and form a carbocation, and then it can attack. Will I get the same product? Yes. But I'll do it by a different mechanism. So primaries always do SN2, tertiaries always do SN1. The problem is the secondaries. Because secondaries can do either one. Because they do form stable carbocations, but they usually don't have enough steric hindrance, so they can also do SN2. So the one thing that we won't necessarily do is we're not going to focus on the secondaries, because the secondaries are really dependent on a number of things. So I'm going to basically create sort of an oversimplified scheme. So primaries, SN2, tertiaries, SN1, secondaries, it depends on what they react with. If a secondary is reacting with a strong nucleophile, it's going to do SN2. What do I mean by strong nucleophile? It has a negative charge. But we don't know any other nucleophiles. Oh, we will. Because is water a nucleophile? Yes, because the oxygen has lone pairs. But it's neutral, so it's weak. Can a weak nucleophile react? Only in SN1, only with carbocation. So for the secondaries, if it's strong nucleophile, it's going to do SN2. If it's a weak nucleophile, it's going to do SN1. And we're going to make a table out of this. So we're going to make a table out of this once we go through these reactions. Okay. But as far as carbocations go, primaries unstable, so unstable they don't exist. Secondaries stable, tertiaries more stable. All right. So that's the importance. And whoever proposed this, and there is no person's name associated with SN1 or SN2. If there was, that person would have solely discovered it, or a couple people would have solely discovered it, and so I don't think they did because there's no name on it. So this came about by everybody basically looking at different aspects of this. So we have the mechanism. My mechanism would never be accepted unless I could show that carbocations were stable. I could show what their structure was, and I could show how their stability affected the rate of the reaction, which we'll have to get to here. So let me just ask this question, and then we'll take our 5-minute break, and then we'll kind of review this with what the PowerPoint notes are, and then we'll talk about other stuff related to SN1 and SN2. What halide do you think reacts the fastest in an SN1? Think about that. When we come back, I printed out new humongous cards, including for people who don't have them. But I remembered I didn't bring my phone. So I have to go get my phone. And this is totally That question is totally, what do you think? Right now, you may not know the answer, so tell me what your gut instinct is.
I just have a question.
Yep.
About the test.
Which test?
That's the question. So
Which test?
for exam 1, it said like, oh, you have a new grade posted. Is
Yes.
that our final grade for
Yes.
exam 1? Okay.
Yes. So yes, I went through and I have your exams right here,
Oh,
but my years of experience tells me don't hand them out until the end.
I just wanted to know if you graded like those 2 questions or you graded the whole
So I,
test.
no, I, only 12 tests. 12 tests is like a piece of cake, considering it's normally like 60. And it's probably extra 2 pages during the year.
My teachers, it's gonna take so long to do my test.
Well, that
But
doesn't
they
mean
only-
I always give them back in the next period, because that sometimes happens, sometimes doesn't. Sometimes it may take me a week to do them. But with 12, yeah, it took me a little bit of time last week because I was occupied with other things. But no, they are done. And so I graded the first 2 questions, whatever you got on that, went back to the first test. I didn't mute those, I just added in the scores for the first test. And if you went over 100, you got some points to play with. Yeah,
So did those questions count for the last test I had for this one?
yes. So they counted for both. So I muted the other questions that I'll give you at the end. Okay. All right, then let's take our break. And the first question I'm going to ask you when I come back, is which kind of halide do you think reacts the fastest in SN1? And your choices are going to be primary, secondary, or tertiary. Or I suppose D, I don't know. But then I'm going to ask you, take an educated guess. Or take a gut guess. What's your gut tell you? Okay. All right, so that's what we're going to start again. The question is, which type of halide do you think is going to react fastest in an SN1 reaction? We'll call A primary, B secondary, C tertiary, and 4, I guess, I can't guess. Okay? So A primary, B secondary, C tertiary. Which one reacts fastest in an SN1 reaction? I think your fingers are overlapping, Sydney. Got it. Okay. Okay, what do we have? Stop. Let's see. Stop. No. Somebody said D. There's one D. So I got 4 secondary, 6 tertiaries, and a D.
Okay, yeah. It's C.
You chose C, so 4 and 7. 4 secondaries, 7 tertiaries. Could I ask why you selected what you did? If you chose one of those? Somebody who chose secondary, why did you choose secondary? Could just be a gut instinct, but if there's anything informing your gut instinct.
You said for tertiaries that there's too much steric hindrance, so it's more difficult to detect. So I just thought by default it was the
Okay, so secondaries have a carbocation, and there's less steric hindrance than there would be. Okay. That's a good gut instinct, which we'll have to talk about. Anybody else with secondaries? Why you chose what you did? Tertiaries? Why did you choose tertiary if you chose tertiary?
I couldn't remember if it was primary or tertiary in the test.
Okay. Will a primary undergo SN1? No, because a primary can't form a carbocation. That's good, there were no primaries.
I picked tertiary because it's the most stable, and I figured the extra root to them would be helpful to the carbocation.
Okay, so it's most stable intermediate. Does a reaction, if a reaction has the ability to form two different intermediates, or does the intermediate stability play a role in the reaction rate? So that's a question for me to explain. How many people say it does, though? What's your gut tell you about that? What's your gut tell you about that? Were you giving me an answer or for a question? Okay. Let's see, up question number 1. So how do I want to ask this question? Do you think that what do you think will react faster? Or no? Does the stability of the intermediate play a role in the rate of the reaction? A, yes, B, no. Does the stability of the intermediate play a role in the rate of the reaction? Yes or no? A or B? Yay, yes. In the overall reaction. So in other words, if I was to ask you which is going to go faster, a secondary halide plus hydroxide or a tertiary halide plus hydroxide, do you think that the stability of that intermediate, secondary versus primary carbocation, is going to play a role in making the reaction go faster or slower? Does the stability of the intermediate play a role? Yes, A, B, no. Or I suppose C could be, it depends. And if you choose C, then I'm going to ask you what it depends on.
So A is yes.
A is yes. So does the stability of the intermediate play a role in okay. 8 say yes, 3 say no. So does it play a role? And so that's the next issue that we should deal with, that we have to deal with. Does it play a role? The only way we can answer this question is by drawing the reaction coordinate diagram. So let's say I start with the same reactant, same energy of the reactant. Is a primary, secondary, or tertiary halide more or less stable? Actually, we don't have rules about stabilities of halides. So for the most part, primary, secondary, tertiary halide are going to be the same energy. So we're going to start them out at the same energy. And then over here, I'm going to be forming as my intermediate a secondary carbocation. And if I wanted to form a tertiary carbocation, where should the energy of the tertiary carbocation go? Should it go above the secondary or below it? The tertiary carbocation's energy, should it go up here or should it go down here? Below? Everybody say below? Why do you say below? So is a tertiary carbocation more or less stable than a secondary? More. So what does that mean in terms of energy? It has less energy, so it should go here. Now what I need to do is I need to draw the coordinate diagram going up to the transition state and down to the secondary and down to the tertiary. But before I do that, what's the energy between the reactants and the transition state? What's that called? That's the activation energy, right? That's EA. That's the activation energy. Why is that important? Because the Arrhenius equation says that the rate is equal to some preset value times e to the minus EA over RT, where RT is the energy form of the gas constant. So the temperature and the activation energy play a role in the rate. Right? This is General Chemistry 101, maybe 102. So what do we know? What do we know about temperature? If you want the rate to go faster, what do you do to the temperature? Increase it, right? Why do we put stuff in the fridge? To slow the reactions of decomposition of the food down by lowering the temperature. So why is that? Because of this math. Is it a linear? No, it's a logarithmic function. So if you double the temperature, you don't double the rate. In general, it's like what? Every time you increase the temperature like 10 degrees Celsius, you double the rate. It's either 5 or 10. But it's not a linear function because it's E, right? 2.303 raised to the whatever power. EA is the same thing, but which goes faster? A reaction with a low activation energy or a large activation energy? Low activation energy. So the lower the activation energy, the faster the reaction. Agreed? Okay. So, rhetorical question here. If you would like to answer, go ahead. But you answer at your own risk. Which reaction is going to have the higher activation energy? Forming the secondary carbocation or forming the tertiary carbocation? That's good. You realized it was going to be a rhetorical question, so nobody jumped in. There's a principle that actually tells us the answer to that question. And it's called, in a textbook, it's called the Hammond, some Leffler principle, but I usually just call it the Hammond's postulate. And Hammond's postulate, when Hammond proposed this, he never thought it would be in organic chemistry taught to college students. Because the actual theory is pretty up there. I mean, I don't remember hearing about it until graduate school. But here's what we can do graphically. So I take a piece of paper. And with my piece of paper, I make a thermoneutral reaction where reactants and products have the same energy level. Where does the transition state occur? At the peak of the paper, right? But where does it occur relative to the reactant and the product? Dead in the center. 50% of the reaction. You have to go 50% of the reaction in order to get to the transition state. Okay? Now, let's make the reaction exothermic Let's make it endothermic to start with. So I'm going to raise the energy up on the products. What happened to the position of the transition state? Where did it move towards? It moved towards the products, right? Because this is the products, this is the reactants, from your perspective. So when I make the reaction endothermic, the transition state moves towards the products. What do you think happens if I make the reaction now exothermic? What happens? The transition state moves towards the reactants. My PhD advisor invested in this huge piece of like metal that was absurdly big for the room, and he would move it back and forth, and it would, be like tin and crinkle and everything else. I haven't invested in that. I only got a piece of paper. But you have a piece of paper if you want to remember that in the future. So what Hammond said was that if the reaction is endothermic, or if it becomes more endothermic, the more endothermic it is, the more the transition state in position and structure resembles the products. And if it's an exothermic reaction, the transition state will resemble in structure the reactants. That's what he said. So we have to make some interpretations about that. First of all, we have to talk about the activation energy. So which one of these two has a higher activation energy? Endo or exo? Endo or exo? Endo. So when you have an exothermic reaction, you have a small transition state energy. Now, in order for me to get to the transition state, what's it going to cost me? It's going to cost me time, and it's going to cost me energy. Because what I have to do is I have to take that structure and I have to move atoms around in order to get it to the transition state. And the more time and more energy it takes, well, the more energy it takes, the longer it's going to be. So we don't necessarily have to interpret it that way. We just have to say, oh, which reaction is going to go faster, endo or exo? Which one's going to go faster? Endo, exo, or same? C, same. So A is endo, B is exo, C is same rate. You might as well ask it if no, you're not fighting to give me the answer, so I guess we'll make everybody come up with an answer. So my question is, which reaction goes faster? Endothermic, exothermic, so endo's A, exo's B, or if they go at the same rate, C. I think your fingers have to. I was going to put little hand things where you could hold it, but I didn't make it that far. 11-0. Exo. Why? Lower activation energy, Arrhenius equation says the lower the activation energy, the faster the reaction. It's all math. Right? But we're trying to do this conceptually. All right, so the Hammond's postulate says that basically we have to know if we're dealing with an endo or an exothermic reaction. But it actually doesn't, that isn't necessary. So by my piece of paper, if I write the transition, if I write the reaction coordinate diagram going to a secondary carbocation, by definition, by what I just did, where should the reaction coordinate diagram go for forming the tertiary carbocation? Will the transition state energy be lower or above what I just drew for secondary? Lower? And the transition state will look closer to the carbocation than the secondary one. So let me erase my activation energy here. And I'll redraw the tertiary. So which one of those carbocations is going to be formed fastest? Secondary or tertiary? Tertiary. So by the Hammond's postulate then, and the fact that we know a tertiary carbocation is more stable than a secondary carbocation, the tertiary carbocation is going to be formed faster. We all in agreement with that? What was my original question? Well, that was. What was my original one? Yeah, that's what I know. That's what I'm trying to remember myself. So what's the original question? The original question was, which halide do you think will react fastest in an SN1 reaction? Does this answer that question? Well, I still need to make one more step. The Hammond's, here's the complete reasoning. And if you look at some of the older exams, when I have lots and lots of students, I'm tempted not to ask this question because then it's an essay question and it takes me a long time to grade. You can depend on whether with 12 students or 11 tests I'm willing to go that far, but here's how I would rationalize the answer to that question. Number one, tertiary carbocation is more stable than secondary because each alkyl group stabilizes the carbocation. The tertiary carbocation is formed faster because it has a lower activation energy according to Hammond's postulate. And by the Arrhenius equation, if it has a lower activation energy, it's formed faster. So what have I just established? A tertiary carbocation will be formed faster than a secondary one. But is that the answer to my question? I need one more link. Let me go back here. Why will a reaction go faster if I form a tertiary carbocation relative to a secondary carbocation? Because the formation of the carbocation is the rate determining step. So because the formation of the carbocation is the rate determining step, forming the more stable carbocation, since it's formed faster, will make that reaction occur faster. From where? So the last portion is, because the rate determining step is the formation of the carbocation, we form the more stable carbocation, or the step that forms the more stable carbocation is going to, the overall reaction is going to occur faster. So it's not just being intuitively obvious that a reaction that forms a more stable intermediate is going to occur faster. It's actually, there are two principles that we have to invoke. The first one, the Hammond's postulate, and the second one, the Arrhenius equation. Now you might say, well, that's an awful lot of details. Well, yeah, but it's not just a gut instinct that the more stable intermediate is going to be, the product from the more stable intermediate is going to occur faster. That's what's going to happen. So then which SN1 reaction is going to occur faster? With a tertiary, then a secondary, and primaries don't undergo SN1. Okay. Just a lot of stuff that goes into this. Everybody kind of with me? Maybe I should make that a take-home quiz question, the essay one. Yeah, it's more stuff to grade. Don't worry. I'll grade it if necessary. I will suck it up and grade all those questions if I need to. But does everybody understand? So there are principles involved here, and we're going to use those again. Because only the next time I go, remember about the Hammond's postulate that if you form a more stable intermediate, the reaction goes faster, and you're all going to go, and I'm going to say, remember that? Yes, you remember that, and I'm going to move on. But that's why. Okay. So, where are we at with SN1? Here's just the formal slides that I did by hand. We got a slow step, we got a fast step. The slow step is forming the carbocation. The overall rate is rate times the alkyl halide concentration to the first power. That makes this a unimolecular reaction, which is SN1, versus bimolecular, which is SN2. Here were the steps that we wrote. We broke the carbon-halogen bond. We formed the carbocation. And then when we formed that carbocation, we had to evaluate what's the stability of the carbocation. Tertiary more stable than secondary. Primary doesn't exist in solution. That's what this was going to be about. Okay. So that means that if we have to form a carbocation to do SN1. So tertiaries react the fastest, secondaries react second fastest, and primaries do not react. It's an awful lot of red with a big hash mark through it. Primaries do not react SN1. Once we form our carbocation, then our nucleophile comes in, and we get a substitution product. So then there's the overall reaction. With step 1, step 2. But in this case, I'm reacting a nucleophile that has a negative charge. So when the negative charge reacts with the positive charge, we're done. What does the reaction coordinate diagram look like? It looks like that. Break the carbon-bromine bond to the first transition state to the intermediate carbocation. Form the nucleophile carbocation bond to the second transition state all the way to the final product. So it's a two-humped camel. Peaks, transition states, valleys, intermediates. Okay, let's make it a little more complicated. Now, when you have a carbocation, you have the extreme nucleophile, the most electron poor. Well, when you have the most electron poor electrophile, any nucleophile that's rich, regardless of its richness, is going to donate to that extremely poor carbocation. So a nucleophile that is not negatively charged but does have lone pairs can donate to that electron poor carbocation. And so what are our weak nucleophiles? Nucleophiles that have electron pairs but do not have a charge. Well, I think I outlined those last week, but that was last week. So here are two. H2O and alcohol. And I write the water and the alcohol like this to show you that there's not much difference between alcohol and water. One carbon group. So that means that an alcohol and water are going to react very similarly. They are both weak nucleophiles because they have lone pairs that they can donate, so they are electron rich, but they're like middle class electron rich. The things with the negative charges, they're super electron rich. But the laws of chemistry are that they must donate to electron poor. So, what would the mechanism be if I wanted to take tertiary butyl chloride and react it with water? Now, the slide before this called this a solvolysis reaction. Basically, for this reaction, what I would do is dump some alkyl halide into water. So the water would be the solvent. So solvolysis means, well, lysis is cleave. So I'm cleaving the solvent molecule in this reaction. This has to be SN1 right now because it's a tertiary halide. I'm going to apply another rule that says water and alcohol can only react in SN1s because they're not rich enough to kick off a leaving group. They can't do SN2. They can only react with a carbocation. So what's the first step in this mechanism? Break the carbon-chlorine bond. What's the transition state going to look like? Well, first thing is what's the product's going to be? I'm going to get a C plus and a Cl minus. The transition state's going to look like what? A dotted line to the Cl. Any charges? And partial positive on the carbon. Okay, so partial positive on the carbon, partial negative on the chlorine, and I'm forming my carbocation. I'm going to write the carbocation down here. Okay. Now my carbocation is going to react with my water. In general chemistry, we would have classified this as a Lewis acid-base reaction because the water is going to donate its pair of electrons to the carbon, to the C+. Okay, so I'm going to take, and again, I have to write these arrows. The arrow from the lone pair on the oxygen is going to be added to the carbon. What part of the water molecule is going to add? The whole thing. So now I form my carbon-oxygen bond. And the oxygen still has one lone pair left over because it used the other lone pair to form the CO bond. Because the carbon didn't have any electrons to share, so the oxygen had to share them both. Now when I do this reaction, the charge total on the left must equal the charge total on the right. So on the left-hand side, what's my overall charge? Sum. +1. Okay.
So when that group, once you break the carbon, you for there's only carbon has 4, but it's missing an electron.
It's missing an owned electron. It has 6 shared electrons. So it's got 2, 4, 6 electrons that it's sharing. It owns one of each of those bonds. So carbon came with 4, it now has 3, so it has a positive 1 charge.
Right, so that fourth one that was known
Is gone.
Chlorine took that.
Yeah, chlorine took it.
Okay.
Chlorine took it. And so now if it wants to form a bond, it's got to find an atom that's going to basically give it both electrons because it doesn't have one to give. Now when that oxygen does that, what happens to it? I've got a +1 charge on the left-hand side. I need a +1 charge on the right-hand side because I can't make or lose charge. So where does the +1 charge go in the product?
So that oxygen that has 3 bonds and you put it in the +2, so would that be one?
Well, that was my question. So where's the plus charge? On the let me ask the question differently. What's the formal charge on the carbon in the product? 0. What's the formal charge on the oxygen? +1. It's sharing and owning 8 total. It shares 6, it owns 2 outright. How many does it own of those? It owns the 2 outright, so there's 2, then 1 in each of the 3 bonds. So it owns 5, but it came with 6, so what happened? It lost an electron, so now it has a positive charge. Where did it lose its electron to? The carbon, because once the carbon-oxygen bond forms, if they are to split up equitably, each atom gets a bond, each atom gets an electron. And that's the way we calculate formal charge. So now I have an oxygen with a +1 charge. What is it called? It is called an oxonium ion. Sort of analogous to the carbonium ion that you can call a carbocation, that I won't. But at least if you say carbocation instead of, what is it? Carbonation or something like that, which is, or no, carbocation. Somebody really mispronounced it when this guy from Case won the Nobel Prize on his work with carbocations. Carbocation chemistry. It's like, He was the guy who was able to add a hydrogen to methane to form 5 bonds and break all the rules. But he also studied a lot of carbocations. So oxonium ion is just an oxygen with a positive 1 charge. Is the oxygen happy? Well, let's come back to the happiness of the oxygen. What's the transition state look like? Did I form a bond? Well, in the transition state, I'm forming a bond, right? So what should go between the carbon and the oxygen? A dotted line. Dotted lines always show us the bonds we're forming or breaking. How about charges? Partial positive on the carbon, partial positive on the oxygen. So there is my transition state to make the oxonium ion. Not in the transition states. Because if you remember, we don't take into account the electron pairs. We only take into account bonds and charges. But where do the charges come from? The presence or absence of lone pairs, but we do not put them. We have no way to do a delta dot. Although you could put delta dot, but we don't. Okay, so in the second step of the reaction, then the whole water molecule adds to the carbocation. Now you could say, but I'm going to form an OH, I'm going to have a COH, why doesn't hydroxide add? And my question to you is, well, how much hydroxide is there in water? If I had a glass of pure water, what would the concentration of the hydroxide ion be? Zero? It's not zero. It's 10 to the minus 7th. Well, there's also 10 to the minus 7th H pluses. Right? So in water, you have the autoionization equilibrium. I know this is general chemistry, but we have to incorporate general chemistry where appropriate. So if I have water that I'm going to add to my reaction, I'm not adding hydroxide, I'm adding water. Is there hydroxide present? Yes, at 10 to the minus 7th concentration. Is that large? No. So what's going to add to my carbocation? The intact water molecule. So the entire water molecule adds to give me that oxonium ion. So you do not, and I'll just leave it at that. Whatever I was going to say you do not do, don't do it. Right? We all understand what to do not do. If you don't ask somebody, because then I didn't tell you. It's like, you told us to do this. No, didn't tell you to do it. We had the entire water molecule. Still with me? Oxonium ion, is it happy? Why not? Why isn't it happy? I had a positive charge on oxygen, and oxygen's what kind of an element? It doesn't like positive charges because it's electronegative. So that oxygen would be much happier. And, happiness isn't part of the chemistry. Stability is. So it would be more happy and more stable if it was neutral. Okay, so what am I going to do then? Well, I got to get this to be a neutral oxygen. So what do I do? What can I do to make that oxygen have a zero formal charge? Let's break the oxygen-hydrogen bond and give that pair to the oxygen. What happens to the H? It leaves as an H+. Now we can actually write this over here as just an H+ ion. Most books like to take that H+ ion and bond it to water. Because it's going to form an H3O+, which is really what it is anyway, right? H+ in water is H3O+. They will go to the extreme, and I don't like to do this, but you could do this if you'd like. They will put another water molecule in here, and they will say, oh, well, this water molecule will then take that H+ off. So the arrow is going from the oxygen to the H+. Now, I'm okay with this if we have an understanding here. And our understanding is that the H+ falls off the molecule and the water's there to catch it. The water is not aggressively ripping that hydrogen off. The water's just catching it as it falls off. And I have to say that because if something comes in and aggressively removes a hydrogen, it's normally a base, and it's normally a very strong base. Water is neither of those. So it's just going to kind of catch the H+ as it falls off. So whether you write this as an H+, or you might see in the book as an H3O+, it doesn't matter to me. But the H+, as it leaves, it's going to be bonded to something. Ellie. So eventually, the H3O+ will connect with the chlorine, maybe. Let's deal with that. So if we're back in general chemistry and I had HCl to H3O or H2O, I would write the products as H3O plus Cl minus. Because that's what would happen. In water, the H plus is going to bond to the other water molecule to make H3O plus, and the Cl minus is just going to be floating around as Cl minus. Is this an equilibrium reaction? Or does the HCl completely dissociate in water? The HCl completely dissociates in water. Why? Because it's a strong acid. And the way we define strong acids are, strong acids completely dissociate in water. Weak acids do what? Partially dissociate in water, which means we end up with equilibrium arrows. And in general chemistry, that means we end up with ice charts. Right? You remember there is such a thing as an ice chart, right? You just don't remember necessarily the ugly details of it. Right? But that's what happens when we have weak acids. But this is a strong acid. So, your question about whether the H3O or the H plus would combine with the chlorine? The answer is no, it wouldn't, because it's like we dissolved HCl in water. Give us another reaction where there's an organic solvent here, not water. The H would combine with the Cl, and you probably see HCl gas coming out of your reaction vessel. We got one more thing, transition state. So without the other water molecule present, what's the transition state going to look like? A partial bond, oxygen to the hydrogen that's being lost. Partial positive charge on. Partial positive charge on. Two partial positive charges? You're right. Two partial positive charges. Because the oxygen is going from +1 to 0. The hydrogen's going from 0 to +1, two delta positive charges. But that's not very stable. I know, it's a transition state. It's not very stable. So that's our mechanism that we would write for a solvolysis reaction. So tomorrow, tomorrow's what? Wednesday? It's moving fast, but not that fast. So tomorrow, if I said, here is a take-home quiz problem, what I would probably do is I could just turn this HOH into CH3OH. And what would you do? You basically copy this mechanism, erase one of the H's, and put a CH3 on it. Could you break the OCH3 bond? No, because if you did, you'd form a CH3 plus, and that's a methyl carbocation, which is even worse than a primary instability. All right. So, and the rest of these slides then are basically showing you that reaction. Now, what kind of reaction coordinate diagram does it have? It's now got a 3-humped. Because how many intermediates do I have? 2. So I've got 2 valleys, and around those 2 valleys, 3 peaks. Right. So we're almost done with SN1. Tomorrow, I think for tomorrow I've put, and when I said yesterday, I put that in tomorrow's folder, but then I didn't release tomorrow's folder. I have released tomorrow's folder. So you'll see, I think we're going into like now chapter 8. So if you want to read ahead, you can go ahead and read ahead. I'm ahead of organizing, so if you wanted to see the video ahead of time, or if you want to see a video afterwards in addition to this one, if there's a video above each PowerPoint, that video goes with that PowerPoint, but we will go from there. I put the answer key to this in yesterday's folder. I did in the afternoon. And so again, the first 2 problems counted for last exam. This exam, I'll unmute this exam. It'll give you an idea where you're at. I will be going through and doing the top hat problems and putting those scores in the next couple days as well. But so far, as we've been doing this, I've been listing the problems. Those are going to be due at the end of the week.